Welcome to today's deep dive. We've got um, a pretty fascinating breakdown in front of us today from a material scientist, and it's all about the incredible and honestly often completely misunderstood world of lab-grown diamonds.
Yeah, it really is a misunderstood topic. I mean, it completely reframes the whole concept of what a gemstone even is.
Right, exactly. So our mission for this deep dive is pretty clear. We're going to completely dismantle the myth that lab-grown diamonds are just, cheap fakes or imitations like cubic zirconia.
Right, because they're absolutely not.
No, not at all. Instead, we're going to explore how they are actually perfect atomic copies, like the ultimate masterpiece of human science. And we'll look at why they are actually the key to our high-tech future.
It's a massive paradigm shift in how we understand materials.
It really is. And I think by the end of this conversation, you'll realize that the diamond in a jewelry store window isn't just a symbol of romance. It might actually be the exact same technology that, eventually powers your electric vehicle or even survives the harsh radiation of deep space.
Which is just a crazy thing to wrap your head around, honestly.
Totally. Because usually when we talk about a diamond, there's this built-in expectation of deep time, right? Geology. You look at a ring in a display case, and the jeweler tells you that the stone took 1 billion years to form.
Oh, absolutely. The whole industry is built on that scarcity, the slow, natural forces of the planet.
But stepping into material science and advanced engineering, well, it breaks that billion-year timeline completely. So before we get into how scientists are basically building these things from scratch in a lab, we have to look at what a diamond actually is at its core.
Yeah, that's where it gets really interesting.
Right, and the source material starts this off with a mind-blowing connection between the pencil sitting on your desk right now and the hardest gemstone on Earth.
Yeah, because when you strip away the marketing campaigns and the velvet boxes, a diamond is made of exactly one thing. It's just 100% pure carbon.
Which is the exact same element that makes up graphite.
Yeah.
Right? Like the dark, smudgy stuff inside a pencil.
Exactly. If you look at them purely through a basic chemical formula, graphite and diamond are identical. They are both just C on the periodic table.
That is so weird to think about.
Right, because obviously one is pitch black and incredibly soft and you can write with it, while the other is perfectly transparent and literally the hardest naturally occurring substance we know of.
Okay, so how can two things made of the exact same ingredient behave so radically differently? I mean, what's the catch?
Well, it all comes down to a fundamental concept in materials science called crystal structure
Okay.
that refers to how the atoms are physically arranged and how they bond to one another. So the secret is entirely in the architecture, not the bricks themselves.
Right, the architecture. So let's picture the architecture of pencil lead first. What are the carbon atoms doing in graphite?
So in graphite, the carbon atoms form these flat, two-dimensional sheets. You can kind of imagine a microscopic chain-link fence made of hexagons.
Okay, I can picture that.
Yeah, and the carbon atoms bond together really tightly within that flat plane. Scientists call these sp2 bonds. But, and this is the key, the connections between the stacked sheets are incredibly weak.
Oh, I see. So the sheets themselves are strong, but they don't hold on to each other very well.
Exactly.
Which completely explains why a pencil leaves a mark. Like when you press down on the paper, you're just sliding those loose sheets of carbon right off the stack.
Yeah, that looseness is the defining trait of graphite. But diamond, on the other hand, uses a completely different architecture.
Okay, so what does that look like?
In a diamond, a single carbon atom binds to 4 surrounding carbon atoms, and it forms a rigid three-dimensional shape. It's called a tetrahedron.
A tetrahedron.
Yeah, and these are known as sp3 covalent bonds. So instead of a loose stack of paper, you can picture a rigid Lego castle that has been basically super glued together in every possible direction.
Oh, that Lego castle image really helps. So every single block is locked into the ones around it, above it, below it.
Exactly. Every single carbon atom is locked into a flawless, three-dimensional, ultimate shared bond with its neighbors. There is no weak direction, no loose sheets to slide around.
Wow.
And that perfect 3D grid is the sole reason diamond achieves its world record hardness.
Which means, I guess, if we want to build a lab-grown diamond, we can't just throw a bunch of carbon into a pot and heat it up. We literally have to force those carbon atoms to build that rigid Lego castle, rather than just taking the path of least resistance and stacking up like flat paper.
Right, because left to its own devices at normal room temperature and pressure, carbon prefers to be graphite. That's its comfortable low-energy state.
That makes sense.
So to get a diamond, you have to convince the carbon to adopt that highly compressed, incredibly rigid tetrahedral structure.
And reading through the source material, convincing is doing a lot of heavy lifting there because actually pulling this off requires two completely different methods of material science that operate on a scale that is honestly hard to even wrap your head around.
Oh, absolutely. The forces involved are extreme. So the first method scientists developed is called HPHT, which stands for high pressure, high temperature.
This is the method that tries to mimic the deep earth, right? Like over 150 kilometers down in the mantle where natural diamonds are born.
Yeah, exactly. And the mantle is a hellish environment. So scientists figured, well, if the Earth relies on extreme heat and extreme pressure to forge these structures, we just need to build a machine to do exactly that.
Sounds simple enough, right?
Right, in theory.
Right.
But in practice, they use a massive multi-axis hydraulic press. And first, they crank the heat up to around 1500 degrees Celsius.
Wait, 1500 degrees? That's hot enough to melt steel, isn't it?
It is. The heat gives the carbon atoms the energy they need to break their existing bonds. But the pressure is the real catalyst here. They have to achieve 50,000 to 60,000 atmospheres of pressure inside the chamber.
The source used an analogy for that pressure that actually made me a little dizzy. It's like taking a fully loaded jumbo jet and balancing its entire weight on the tip of your thumb.
Yeah, imagine that concentrated mechanical force. So they place a tiny amount of carbon inside the press, heat it up, and then crush it with the equivalent weight of that jumbo jet.
That's insane.
Under that immense pressure, the carbon atoms physically cannot remain in those wide, flat graphite sheets. They are literally forced to condense and lock together into that tight 3D diamond tetrahedron just to take up less space.
It's just pure brute force physics. But the source material points out that while HPHT is an amazing engineering feat, there is a second method that has material scientists much more excited.
Oh, definitely.
And it's called CVD, or chemical vapor deposition. And apparently this doesn't use a giant crushing press at all.
No, not at all. CVD represents a completely different philosophy of creation. If HPHT is muscling carbon into submission, CVD is coaxing it into existence, literally atom by atom.
Okay, so how does that work?
It takes place in a vacuum chamber, specifically a plasma chamber that functions a bit like a high-tech microwave oven.
A microwave.
Yeah. Scientists place a tiny sliver of diamond, they call it a seed crystal inside. Then they pump in hydrogen gas and methane gas. And methane contains carbon.
Okay, so we've got carbon floating around in a gas, but how do we get those atoms out of the gas and onto that little diamond seed?
They blast the gas with incredibly powerful microwaves. The energy from the microwaves is so intense that it turns the gas into a plasma state.
Wow.
It literally rips the methane molecules apart, severing the bonds between the carbon and hydrogen atoms. So now you have these free-floating carbon atoms raining down inside this chamber.
And they just fall into the seed.
Exactly. Because the seed is already diamond, its surface is a perfect atomic template. So as the free carbon atoms drift down, they land on the seed and snap into place, continuing the exact same 3D structure.
That is so cool.
It really is. Think of it like a highly advanced 3D printer working at the atomic level, or, like watching frost slowly form on a window pane. It methodically builds up, just layer by layer.
So wait, the HPHT method is basically trying to wrestle the carbon into a diamond using the weight of an airplane. But CVD is just carefully stacking atoms from thin air using gas and microwaves.
Yeah, pretty much. And the control CVD gives you is revolutionary. For one, you don't need a room-sized hydraulic press. But more importantly, you can control the purity to an absurd degree.
Purity, like flaws in the diamond.
Right. Natural diamonds pulled from the ground almost always have impurities, like nitrogen or boron atoms that got trapped in the magma millions of years ago.
Oh, sure.
But because CVD builds the diamond atom by atom from purified gas, you can grow a diamond that is chemically flawless.
Wow, that makes perfect sense. And once they pull off this atomic 3D printing, they aren't just cutting these stones and sending them to the jewelry counter, they're taking them into testing labs.
Exactly.
Because apparently when you create a perfectly pure diamond, it behaves in ways that sound like pure science fiction.
Yeah, to a material scientist, a flawless diamond isn't just a gemstone. It is an engineering miracle that pushes the boundaries of physics. It possesses what we call ultimate physical properties.
Let's look at how this atomic perfection actually behaves when you take it out of the chamber, starting with hardness. Because on the Mohs scale, which measures mineral hardness from 1 to 10, diamond is the only 10.
Right, it is the absolute maximum. A diamond can scratch any other material on Earth, but nothing else can scratch it except another diamond.
Which makes it incredibly useful for industrial cutting and drilling. Right.
Oh, absolutely. But the hardness isn't even the most surprising part. The way a diamond handles heat, its thermal conductivity really messes with your head.
Yeah, the source had some crazy stats on that.
Well, diamond has a thermal conductivity of roughly 2,000 watts per meter Kelvin. To put that in perspective, we use copper in our electrical wires and our kitchen pans because it's incredibly good at conducting heat.
Right.
Copper has a thermal conductivity of about 400.
Meaning diamond is about 5 times better at transferring heat than copper.
Exactly. That rigid, tightly packed Lego castle structure allows heat vibrations to travel through the crystal almost instantly without losing energy.
The source outlines a mind-bending experiment you can do to prove this. If you place a flat plate of lab-grown diamond on the table and rest an ice cube on top of it, the ice cube melts instantly.
Yeah, it looks exactly like you've dropped the ice onto a hot frying pan.
It looks like a magic trick. But the diamond isn't hot.
No, it's just sitting at room temperature.
That is so wild.
But the diamond is so ruthlessly efficient at moving heat that it instantly sucks the ambient thermal energy from the room or from the table it's resting on and funnels all of that energy straight into the ice cube.
Oh, wow.
And that's actually why a real diamond always feels icy cold when you touch it. It is physically draining your body heat away faster than almost anything else you can touch.
Okay, this is where I start to get a little confused because there seems to be a paradox here. Usually, things that conduct heat really well, like copper, steel, or aluminum, well, they're metals. And metals also conduct electricity. But the source says diamond completely blocks electricity, pointing to something called a band gap of 5.5 electron volts, or EV.
Yeah, to give you a comparison, silicon, the material inside all our computer chips, has a band gap of only 1.1 EV.
Wait, what exactly is an electron volt in this context? Let's break that down for everyone.
Sure. You can think of the band gap as a hurdle that an electron has to jump over to carry an electrical current. The electron volt is just the measurement of the energy needed to clear that hurdle.
Okay, a hurdle.
Right, so silicon has a tiny hurdle of 1.1. It's very easy for electrons to jump over and conduct electricity, but diamond's hurdle is a massive 5.5.
So you basically need an enormous amount of energy just to force an electron to move in a diamond.
Exactly. It goes back to our atomic structure. In metals like copper, heat and electricity are both carried by free-floating electrons. Because the electrons are free to roam, the metal conducts both.
Okay.
But in our diamond Lego castle, every single electron is permanently locked down into those super tight bonds. There are no free electrons.
Ah, I see.
So that massive 5.5 EV hurdle means electricity simply cannot flow under normal conditions. It is a nearly perfect electrical insulator.
But wait, if there are no free electrons jumping around, how is it moving the heat so incredibly fast?
That's the cool part. The heat moves mechanically through tiny physical vibrations in the lattice. Because the atoms are packed so rigidly together, heating one side causes the atoms to vibrate. And that vibration instantly ripples through the entire 3D structure like a physical shockwave.
Oh, wow.
Yeah, it conducts heat purely through mechanical vibration while completely stopping electrical current in its tracks.
It's acting like a superhighway for heat, but an impenetrable wall for electricity.
Exactly.
And according to the source material, that specific combination is the exact solution to the biggest bottleneck in modern technology today.
It really is. I mean, we are currently living in the silicon age. Every smartphone, laptop, electric vehicle, and server farm runs on silicon semiconductors.
Right.
It has served us incredibly well, but silicon is hitting its physical limit.
Because of the heat.
Primarily heat, yeah, and voltage. When you push too much power through a silicon chip, or if it gets too hot, it physically breaks down.
Oh, because of that tiny hurdle.
Exactly. That narrow 1.1 EV band gap means that at high temperatures, the hurdle gets too easy to clear. Electrons just start jumping everywhere uncontrollably, and the chip short circuits.
That makes sense.
That's why your laptop needs a fan and why data centers spend millions on giant cooling systems.
Enter the diamond.
Exactly. Diamond is the ultimate power semiconductor. It survives incredibly high voltages without breaking a sweat because of that massive band gap. And crucially, it sheds heat instantly through those mechanical vibrations.
So if you use a diamond semiconductor, you wouldn't even need bulky cooling systems. The chip would just whisk the heat away all by itself.
Yeah. Replacing silicon power chips with lab-grown diamond wafers has staggering implications. Let's take electric vehicles, for example.
Okay.
Currently, EVs lose a lot of energy as heat in the power conversion process, and they have to carry heavy, complex liquid cooling systems just to keep the silicon chips from melting down.
But if you swap those out for diamond chips, you can handle much higher voltages safely and waste almost zero energy as heat.
Exactly.
Plus, you get rid of the heavy cooling system, which lightens the car. So the driving range of the vehicle drastically extends on the exact same battery.
It's a game changer. And it scales up to the macro level, too. Think about the global electrical grid.
Yeah, we lose a ton of power there,
A
right?
massive percentage. As power travels from a power plant to your house, we lose it purely as heat radiating off the transmission wires and transformer stations. With diamond-based power controllers, that power loss drops to almost zero.
Wow, we're talking about revolutionizing global energy efficiency here.
Absolutely. And then there are applications where failure just isn't an option, like space exploration. Deep space is flooded with high-energy cosmic rays.
Right.
If a cosmic ray hits a silicon computer chip on a Mars rover, it can flip a bit, corrupt the data, or destroy the processor completely.
Because the radiation just knocks the electrons right over that tiny 1.1 eV hurdle.
You got it. But a diamond-based computer wouldn't even flinch. The radiation can't easily break those strong bonds or overcome the 5.5 eV band gap. A diamond chip is essentially invincible to the extreme environments of deep space.
So, to put this all in perspective for you, the lab-grown diamond you see in a mall display case isn't just an affordable alternative to a mined diamond. You are actually looking at the exact material that's going to upgrade our global power grids, vastly improve our electric vehicles, and send our computers safely to Mars.
It really is the hardware of the future, just sitting right there on a velvet cushion.
It's incredible.
The aesthetic beauty of the gemstone is really just a byproduct of its structural perfection. We've spent decades figuring out how to master the atomic arrangement of carbon, and now we are at the point where we can mass produce the ultimate material.
It's absolute proof of humanity's ability to manipulate the physical world at the most fundamental level.
Oh.
I mean, we took pure carbon, literally the stuff of soot and pencil lead, and we figured out how to perfectly reconfigure it. Whether that means crushing it with the force of a jumbo jet, or gently raining it down in a microwave plasma chamber to build an atomic superstructure.
It takes the magic out of the deep earth and puts it directly into the hands of engineers.
Well said. As we wrap up this deep dive, I want to leave you with a final thought to chew on. We've just spent the last 20 minutes exploring how human engineers completely synthesized the hardest, most extreme natural material on Earth, just by using pressure, gas, and microwaves.
Yeah.
So if diamonds, the ultimate billion-year-old gemstone, can be grown in a lab and perfected to power high-tech computers, what other natural limits in our world are actually just engineering problems waiting to be solved? If we can perfectly grow a diamond from thin air, what everyday material will materials scientists fundamentally reinvent and mass produce next? Something to think about the next time you pick up a pencil.